Great. So, third talk of this wonderful session. So we will have Panos Charalambous, sorry, I can do this, Charalambous, and he will tell us about null infinity as an inverted extremal black hole horizon. Please go ahead.
Okay. All right, so hello everyone, thank you. I'm very happy to be here to share with you our research and also get your feedback. So I'm very grateful to the organizers and the scientific committee. So what I'm here to talk to you about, but actually I'm here to mostly raise awareness about the correspondence that refers to two null surfaces that have consistently appeared in holographic approaches to gravity. One null surface is that of a horizon, the other refers to null infinity of asymptotically flat spacetimes. So this is a work done as part of this black hole project, PI'd by Laura Donai, and also in collaboration with Shreyansh, a final year PhD student at CISA. So still this is unpublished work, but we are estimating for it to be released soon. All right, so let me start with one set of the correspondence that referring to the black hole horizon. So quick review about physics near the horizon. One can always write the geometry near the horizon locally in this asymptotic expansion around distance from the horizon. Right, this expansion takes this form using this Gaussian null coordinate system here to make things a bit simple. And this expansion is an expansion in this coordinate rho here. So rho is like a distance from the horizon, if you would like. And all the other fields that appear, like a kappa, theta, or omega EB, lambda EB, these are some fields that depend on both the advanced time coordinate and this XA coordinates that chart cross-sections of the horizon. So we loosely call these XA directions as spatial directions. So whenever I say spatial, we really mean along these cross-sectional directions. Good, so these subletting, these fields in the metric acquire nice geometric interpretation. For instance, this kappa here in the GUU can be interpreted as a surface gravity, in the sense that it is the non-affinity coefficient on the null normal on the horizon. This omega idea will refer to as the horizon metric, right? And these other fields also acquire a nice extrinsic geometry interpretation. This theta, for example, is of diagonal terms here, good. Capture rotational properties of the black hole as encoded in the so-called twists or Haji-Sekwan form. And the subletting terms in the spatial metric capture the transversal deformation rate tensor. All right, so each of these objects satisfies an evolution equation. For example, the twist band form satisfies the Damour equation, and the transversal shear satisfies the, what is having called the transversal deformation rate evolution equation. Not very creative, really. Right, now the time dependence of the horizon metric is encoded in the expansion and the shear of the null normal, of the horizon. Well, so the horizon have spherical structure, but more interested in a subclass of horizons called non-expanding horizons. And as the name suggests, a non-expanding horizon is one for which its expansion is vanishing on the horizon. And here's the definition, which has two more requirements. One is a topological requirement, which, for example, excludes the Minkowskian light cones from being expanding horizons. And the other is a requirement about some vanishing behavior of Ricci tensor components. Relativistically, this can be interpreted as an energy condition on the matter field near the horizon. So the definition implies then that the null normals to a non-expanding horizon are, besides twist-free, also expansion-free and shear-free. In other words, the horizon metric is stationary. Right, and that's not the horizon metric is stationary. Yeah, that's sufficient. Okay, good. Now the other side of the correspondence is null infinity of an asymptotically flat spacetimes. So let me quickly review this geometry. In Newman-Uti gauge, the geometry of an asymptotically flat spacetime can be written in this form, like here, where rho is some radial like distance. And once one fixes the boundary conditions of this spatial metric, this curly H, AB, then the hypersurface equations dictate the following behaviors of the other metric components. The data associated that describe this asymptotically flat spacetime consists of some initial conditions on some fields entering the metric, namely this Bondi angular momentum aspects, and also the subleading terms in the special metric. This is well known for symptotically flat spacetime, but also has some free data capturing radiating degrees of freedom as encoded in this gravitational shear. Now, as was remarked recently by Ashtek and Speciale, Null infinity can be incorporated in the framework of non-expanding horizons. And more explicitly, Null infinity is a non-expanding horizon of the conformally completed spacetime. Another remark here is that this remains true even in the presence of radiation, assuming a sufficiently fast fall-off of the energy momentum tensor. Now, the existence of preferred divergence with conformal frames and also the boundary conditions of the metric fields imply that the Null infinity is in fact an extremal and non-twisting non-expanding horizon. And this brings to this result that I think it's not well known enough, that Null infinity and black hole horizons can be understood as being conformally isomorphic to each other. And what I mean by this is that if I perform this spatial inversion, where rho here is this near Null infinity radial coordinate you would like, and rho is this near horizon radial coordinate, then the two geometries precisely get mapped onto each other. In the more helpful form of a dictionary, one can say that the geometry in Null infinity is dual referring to this spatial inversion, dual to an extremal black hole, that is, but besides extremal, that is a non-expanding horizon, and also a non-rotating horizon. Good, and this correspondence also gives us more information about what the horizon metric of this dual black hole is. If it's related to this asymptotic spatial metric near Null infinity, it is typically taken to be the sphere, and not necessarily. And also, the gravitational shear acquires the near horizon interpretation of this transversal shear. What of caution here, however, is that this correspondence refers to two geometries that do not need to reside in the same spacetime. A very nice counterexample to this is the four-dimensional extremal Rutherford-Norton black hole. Here is a metric of this extremal Rutherford-Norton black hole, where the discriminant function delta is this perfect square, and then is the mass of the black hole. As was demonstrated by Couch and Torrens back in the 80s, the extremal Rutherford-Norton black hole has a discrete conformal isometry, which is a spatial inversion of the form I just described. But even more interestingly, this conformal isometry is in fact an isometry of the conformal geometry. So this is a nice fun fact. In more practical terms, the Couch-Torrens inversion can be understood as a reflection of the tortoise coordinate that reflects the photon sphere. And this reflection of the tortoise coordinate is precisely indicative of this matching of matching of the event horizon with Null infinity under this Couch-Torrens inversion. Good now, but in contrast to the generic correspondence I was referring to before, this is all, everything now happens in the same space-time. So in the language of this horizon Null infinity correspondence, the extremal Rutherford-Norton black hole gives us an example of a self-dual geometry. And the fact that this self-duality now can be used to say something physical. So let me focus to the simple case of a massless sphere perturbations of extremal Rutherford-Norton black hole. The aim is to see what the Couch-Torrens tell us at the levels of some form of charges. So let me split the problem, the linearized problem, into two parts, each referring to the two null surfaces of interest. Okay, so on the one side, everything in red refers to solving the equations of motion in a near Null infinity adapted coordinate system. In other words, in this regime, one can expand the scalar field to this near Null infinity 1 over R modes. And everything in blue now refers to solving the, again, it's the same equation of motion but in a near horizon adapted coordinate system. In other words, in a regime where the scalar field admits a near horizon asymptotic expansion in this rho to the power n. As is well known, each of the two null surfaces is equipped with its own infinite tower of conserved charges, linearly conserved charges. From the null infinity perspective, one has the well-known Newman-Penrose charges, And solving the equation of motion, one can show that these Newman-Penrose charges are some linear combinations of these near infinity modes. Similarly, from the horizon side, one has the Aretakis charges themselves being expressible in terms of some linear combinations of these near horizon modes of the scalar field. Now, to see what the Cauchy-Lorentz inversion implies, one first observed the very crucial property that the scalar wave operator transforms homogeneously under the Cauchy-Lorentz inversion. And in fact, this transformation is precisely compatible with the conformal transformation of the scalar field itself. In other words, if I am able to solve the near horizon equations of motion, exactly, then the Cauchy-Lorentz inversion outputs a solution of the near null infinity equations of motion. So the Cauchy-Lorentz inversion provides us with a matching condition between near null infinity modes and near horizon modes. Unfortunately, this matching condition then, after some manipulation, this directly implies that evidently the Newman-Penrose charges are in fact exactly equal to these near horizon Aretakis charges. So let me finish with one last technical slide. So we were able to extend this analysis to high spin perturbations, integer spin perturbations, where we also include previously known results and also the new results associated with gravitational perturbations of the extremal Western Northern black hole. Okay, so again, we spare you the details. The take-home message is that the Cauchy-Lorentz inversion provides with a matching condition between near null infinity and near horizon modes, and that this matching condition is precisely such that the near null infinity Newman-Penrose charges are exactly equal to the corresponding near horizon charges. So, in summary, what I wanted to do is emphasize the existence of this correspondence between null infinity and horizon geometries, which there's two types of geometries generally living in different spacetimes. For the special case of the self-dual Western Northern black hole, extremal Western Northern black hole, this duality that comes in from the special inversion is also known as the Cauchy-Lorentz inversion. And the existence of this Cauchy-Lorentz inversion has very physical implications, which we have studied at the level of these near null infinity Newman-Penrose charges and these near horizon Aretakis charges. Okay, so lastly, some possible future directions. Well, there are various aspects one can look at, some of which we're already working on. For example, in the spirit of this matching of near null infinity, near horizon stuff, we are interested in see whether we can match asymptotic symmetries near the two null surfaces. And more interesting question will be whether one can uncover a larger symmetry structure for black holes that is akin to this W1 plus infinity that people have unveiled for asymptotically such spacetimes. And well, eventually, I'll leave it here as with a question mark. It would be very nice to see whether one can construct the holographic proposal for each of the two null surfaces. For example, whether one can construct a celestial holography program with another near horizon holographic proposal, which have been known in the literature as the KCFT. But it's a very open question, and we don't really have a very clear picture on how to do this, so please, any feedback is very appreciable. Okay, thank you for your time, and enjoy the rest of the conference.
Okay, questions? I see someone there. Up there.
I would say that the extremal horizon doesn't correspond to null infinity because the presence of perturbations generate a singularity at the extremal horizon, and they don't do this for null infinity.
Yeah, that's true. The physics are completely different. Null infinity has very different physics from the horizon. That's true. And that's really reflected by the two are not isomorphic, they're conformally isomorphic. So this conformal transformation changes the physics near the two surfaces.
Is it possible to define a scattering problem near the horizon? Like, could you define asymptotically free states, like free states?
Yeah, I don't know how to do this in this strong regime near the horizon.
Because that's something which is special to null infinity, right?
Right, yeah. Right. I mean, we would like to understand something like that, and this correspondence of this format right now I don't have a good answer to the question.
I'll ask that question. Thank you. I also had this question about like the fact that well, I have two questions. So one is
Okay.
a follow-up to the first one.
Yes.
About the fact of like what does it mean like that these Arataki charges
Right.
are related to this Neumann-Penrose charges, because the Arataki ones are usually associated to an instability
Yes,
of the
that's
extremal
true.
horizon. So
Right.
can you say a little bit more like what does it mean? Like how are you interpreting that these two things are related?
Well, I mean, the statement here is that the two are identical because of this existence of this Gauss-Lorentz inversion. But physically, right, the Arataki charges are associated with some linear stability in the extremal black hole. On the other side, Neumann-Penrose charges are clearly not associated with any instability. But yeah, what I'm saying here is just that they are mismatching. That's it, really. Nothing other physical.
And then I guess the second question is how specific is this to like 4 dimensions in a sense?
Not at all, but higher dimensions already in asymptotic flat space-time are more complicated, even though. Okay, good. So the black hole is nothing changing really from the black hole side. But from the asymptotically flat side, things change in the sense that what one will capture as a gravitational shear does not enter, well, in the particular field I showed. So in this sense, this gravitational shear will not be dual in this special inverter sense, will not be dual to this transversal shear on the horizon. So this is not a higher dimension, it's only 4 dimensions.
Okay. Thank you. Is there any other question? No? Okay, so let's thank Panos again.